I'm going to take you through the solutions to a grade 12 advanced functions final exam that I've given in the past. Here's a breakdown of the exam. You can see there's going to be questions about multiple choice, polynomial functions, exponentials and logarithms, trigonometry, rational functions, and then it'll finish off with a problem solving section. And the exam's out of 104 marks. Follow along as I show you how you can get full marks on an exam like this. Let's start with multiple choice. Question 1. End behavior of this polynomial function. Well, I know if I want the end behavior, I just need to look at the highest degree term. The highest degree term is negative 5x to the 4. That's an even degree with a negative leading coefficient. Based on the fact that this function has a negative leading coefficient, I know that as x goes to infinity, y is going to negative infinity. It's going down to the right. And because it's even degree, I know the function starts and finishes on the same side of the x-axis. So as I move to the left, the function must be going down as well. So you can tell from my diagram here that the end behavior is that it goes from quadrant 3 to quadrant 4. So my answer is C. Number 2, which of the following is an odd function? We'll have to be careful here. It doesn't say what's an odd degree function. It just wants to know what's an odd function. Odd functions, all of the terms in the function are odd degree. Well, I see in part A, I have a degree 2 term, which is even degree, so it's not A. In C, I see a constant term, which we consider an even degree term, right? It's degree 0, so it's not C, which means it's definitely not D, which means it must be B. And if we look at B, notice we have degree 5 and degree 1. Both are odd degrees, so that makes it an odd function. Number 3, which of the following graphs corresponds to this function right here? Well, this function, if I look at the highest degree term, once again, it's even degree with a negative leading coefficient, so I know it goes from quadrant 3 to 4. And there's only one of these graphs that goes from 3 to 4, and that's B. Number 4, least possible degree of this function. Well, I need to look at two things. I need to look at the number of turning points. I know the degree is at least one more than that. I see on this graph 1, 2, 3 turning points. So this function must be at least one more than that. It must be at least 4. But I have to check one other thing. I have to make sure that it's at least equal to the sum of the orders of the x-intercepts. If I zoom in on the graph, I see 2 x-intercepts, and both of those x-intercepts, it looks like it goes straight through like a linear function, so those are both order 1. So if I add those orders together, I get 2. When checking both of those pieces of information, whatever the bigger number is, so 4, I know my function has to be at least that degree. So it has to be at least degree 4, so my answer is B. 5, if I want the remainder, when I do this function divided by that one, all I have to do is use the remainder theorem, which says take the 0 of the divisor, so the 0 of x plus 1 is negative 1. I need to take that value and sub it in for x into the dividend, and that will tell me what the remainder would be. So if I evaluate this function when x is negative 1, I would get 1 plus 5 plus 2, which is 8. So I know if I divided those two, I would get a remainder of 8. Number 6, the polynomial 8x cubed minus 27 will factor into, well, I notice that this is a difference of cubes. Right? 8 is a perfect cubed number, so I could think of this as a 2x being cubed, and 27 is a perfect cubed number, it is a 3 cubed. So I have a difference of cubes, so I can just follow the difference of cubes formula, which I will write here for you. And in that formula, just replace a with 2x, so I'll change each of those a's to 2x, and if I replace b with 3, change each of these b's to 3, well, that would lead me to this answer right here, 2x minus 3 times 4x squared plus 6x plus 9. So my answer is B. 7, which of the following divisors is a factor of this polynomial? Well, whichever one of these is a factor of that polynomial, when I plug in the 0 of it into this polynomial, it'll give me an answer of 0, meaning that if I were to divide them, I would get a remainder of 0. That's what makes it a factor. So let me just jot down what the zeros of each of these are. It'd be 1, negative 3/4, negative 1, and negative 4/3. So basically, I would just one by one check those in this polynomial and find out which one makes it be 0. I'm pretty sure an x value of negative 1 makes this be 0. Let me just check that out. So this would give me 3 minus 1 minus 14 plus 4 plus 8. So that would be 2 minus 14 is negative 12, plus 12, that's 0. So yes, x plus 1 is a factor. If I were to divide them, I would get a remainder of 0. Number 8, which logarithm statement below is equivalent to the exponential statement 3 to the 4 equals 81? Well, I know a logarithm is a way of finding an exponent. So I know the exponent 4 is going to be the answer to the logarithm. So I know log of some base and some argument is going to be equal to 4. I take the base of the power and I make that the base of the logarithm, which means that 81 is going to be the argument of the logarithm. Right? This logarithmic statement right here means that 3 to the power of 4 is equal to 81. And that's exactly what the exponential equation tells me. And I see that right here. That's D. Let's move on to 9. Evaluate log base 3 of 9. Well, what does that expression mean? It means 3 to what exponent is equal to 9. That's what a logarithm does. It finds what exponent goes on the base to get the argument. Well, what exponent can I put on 3 to get 9? The answer is 2. 10. The pH of a solution with a hydronium ion concentration of 0.04 moles per liter is, well, to calculate pH, you just have to know the pH formula, which is equal to negative log of the hydronium ion concentration. So for this question, we just have to do negative log of 0.04. And from my calculator, I know that is A, 1.4. 11, convert 300 degrees to a radian measure. Well, if I want to convert a degree to a radian measure, I just multiply by pi over 180. And I could reduce this. 60 goes into both 300 and 180. It goes into 300 5 times, into 180 3 times. So I have 5 pi over 3, which is A. 12, we want to convert radians to degrees. Well, to do that, we just take the radian measure and multiply by 180 over pi. Cancel the pi's. 180 divided by 4 is 45. So I just have 5 times 45, which is 225 degrees. B. 13. Use special triangles and the cast rule to determine the exact value of cosecant of 5 pi over 3. Well, cosecant of 5 pi over 3 would be equal to 1 over sine of 5 pi over 3. And now let me draw a little diagram. 5 pi over 3 is in quadrant number 4 with a reference angle of pi over 3. And if you know your special triangles, I'll just sketch it right here for you. I've got side lengths of 1 to root 3. I know sine from that reference angle would be opposite over hypotenuse, so root 3 over 2. But based on cast rule, I know that in quadrant number 4, only cosine is positive, so sine will have to be negative. So I know this would be equal to 1 over the negative of sine of its reference angle. And sine of the reference angle, pi over 3, is root 3 over 2, so I'll get 1 over negative root 3 over 2. Dividing by a fraction, flip and multiply, I get negative 2 over root 3. That's B. 14. What's this the graph of? Well, based on its shape, you should be able to narrow it down to it being either cosecant or secant. I can get rid of cotangent or tangent. I know that's not the shape of those ones. So I have to decide, is this the graph of cosecant or secant? Well, the graph of cosecant, I know cosecant is 1 over sine x, and secant is 1 over cos x. So let me just sketch the graph of sine x quickly. Sine x looks like this. And this should show you that the blue function is the reciprocal of sine, right? Whenever sine is 0, I see that it's 0 here, 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 and here. 1 over sine will be 1 over 0, which is undefined, which is why we see a vertical asymptote that goes through the x-intercepts of sine, which means that this is the graph of the reciprocal of sine. It must be A. 15, which statement below is true about this rational function? And I see it's giving me information about the asymptotes and the x and y intercepts. So maybe let me just find that information first. So the vertical asymptote is always going to be at x equals whatever makes the denominator 0. So in this case, -1. The horizontal asymptote, because the numerator and denominator are same degree, I just divide their leading coefficients. 3 divided by 1 is 3. X-intercept, I would just set y equal to 0 and solve. If I did that, I would get 2/3. And y-intercept, I would just set x equal to 0 and solve for y. If I did that, I would get -2. So which of these has a correct pair of information? I see that it's B again. Vertical asymptote at x equals -1 and a y-intercept at -2. Number 16 says, using a surrounding interval, a good estimate for the instantaneous rate of change of the temperature at 10 minutes would be, well, if I want to use a surrounding interval like the question implies, I would need to look at the information before 10 minutes and the information after 10 minutes and find the average rate of change between those 2 points. So let's find the average rate of change between 8 and 13 minutes. The average rate of change, I could use m to communicate that. I would do the change in y. What did the y change by? It went from 205 to 290. So I'll do 290 minus 205 as my change in y. And my change in x, it went from 8 to 13. So I'll do 13 minus 8 to get my change in x. So I have 85 over 5, which is 17. And do I see that as an option? Yes, part D. All right, that's multiple choice done. Let's move on to some short answer questions. Section 2 is all about polynomial functions. I'll complete this chart and sketch a possible graph of this function that I see is in factored form. First of all, what degree is this function? Well, if it's in factored form, you just add up the exponents that are on the factors of x. So I just have to do 1 plus 2 plus 3, which is 6. So this is a degree 6 polynomial function. To find the leading coefficient, I have to multiply any constant factor, so -1/2, times all of the coefficients of the x's within each factor. So I have to do -1/2 times 1 times 2 squared times 1 cubed. Let me write down that calculation I would be doing. -1/2 times 1 times 2 squared times 1 cubed. If I do that calculation, I get -2. So the leading coefficient is -2. I have even degree negative leading coefficient. That came up earlier. That's quadrant 3 to quadrant 4. X-intercepts. Well, I just have to look at, because this is in factored form, what would make any of those factors be 0? X plus 4 would be 0 if x was -4. 2x minus 3 would be 0 if x was 3 over 2. And x plus 1 would be 0 if x was -1. So let me write down those x-intercepts. And the question also wants me to state the order of each of these x-intercepts. To find the order, I just look at the exponent that is on the factor that created the x-intercept. So the order of the x-intercept of -4, I just look at this exponent right here, it's 1. The x-intercept of 3 over 2, I look at this exponent, it's 2. And the x-intercept of -1, look at that exponent, it's order 3. To find the y-intercept, I just evaluate f at 0. I literally just sub in 0 for all the x's and see what I get. So I would have -1/2 times 4 times -3 squared times 1 cubed. And that would give me -18. So my y-intercept is at 0, -18. With all of this information, I should be able to make a rough sketch of this function. I'll start by plotting the x-intercepts at -4, 1.5, and -1. I'll plot the y-intercepts down at -18. Well, I don't have a scale on the y-axis, so I can put that anywhere and just label it as -18. And now I just need to follow the correct end behavior. It needs to go from quadrant 3 to quadrant 4. So I know I need to start down here and finish down here. And at each x-intercept, I need to make sure, based on the order, to make the correct shape. The order tells me what power function it's going to look like. So order 1, it needs to look like a straight line. Order 2, it needs to look like a parabola. Order 3, it needs to look like a cubic function. So at -4, I need to go straight through the x-intercept. At -1, it was order 3. So as I get close to -1, I'm going to approach it to the left. And then I'm going to curve through where the function turns just about horizontal right at that point when x is -1. And then curves back down. And then at 1.5, it needs to bounce off like a parabola. So there's a rough sketch of my polynomial function. 18 says find an equation in factored form for this degree 5 polynomial whose graph is shown. Well, I'll start off by making a formula for the family of functions that has those x-intercepts. I'm going to put a scale factor of k in front of those factors, and I'll have to solve for that value of k that makes this function go through the point that we see that it goes through. But let me first figure out the factors. So I need to look at the x-intercept of -2, and I figure out what factor would have a 0 of -2, and that would be x plus 2. And based on the fact that it looks like a degree 2 power function at that x-intercept, right, it looks like a parabola, I know this must be an order 2 x-intercept. There's an x-intercept at 0. What factor would create an x-intercept of 0? Well, that would just be a factor of x. And then lastly, there's an x-intercept of 3. A factor of x minus 3 has a 0 of 3. And it looks like a degree 3 power function at that x-intercept. So I know this is order 3. What I have to solve for now is what's the value of k that makes this function go through that point. That point has an x and a y value. So I'll replace y with 6, and I'll replace each of the x's with 1, and then solve for k. So I have 3 squared, which is 9, times 1, times -2 cubed is -8. So I have 6 equals -72k. If I divide that 72 to the other side, and I can reduce that fraction. 6 goes into 72 12 times, so I can reduce this to -1 over 12. So my final equation would be p at x equals -1 over 12 x plus 2 squared x minus 3 cubed. 19, it says use long division to divide those two expressions, and we'll express the answer in quotient form. So let me set up the long division table. And how I do long division, I look at the first term of the dividend and divide it by the first term of the divisor. 6x cubed divided by 2x is 3x squared. I then multiply the quotient 3x squared by the whole divisor 2x plus 1 and write the answer down in the dividend. 3x squared times 2x is 6x cubed, and 3x squared times 1 is 3x squared. I then subtract the like terms in my dividend. Notice I lined up my like terms to make this simpler. The 6x cubes cancel each other out, and x squared minus 3x squared is -2x squared. I can then bring down another term in my dividend and repeat the process until I'm done. -2x squared divided by 2x is -x. Multiply that -x by the whole divisor. I get -2x squared minus x. When I subtract the like terms, I'm left with -12x. Bring down the 5 and repeat one last time. -12x divided by 2x is -6. Multiply that -6 by the divisor to give me -12x minus 6. Subtract my like terms, and I'm left with a remainder of 11. So I can write this in quotient form by writing the dividend divided by the divisor is equal to the quotient plus the remainder over the divisor. 20 asks us to use synthetic division to divide those two expressions and express the answer using the multiplication statement. So synthetic division, let me just set up a synthetic division table. I find the 0 of the divisor, so what makes x plus 2 be 0 is -2. I write that here. And then I write the coefficients of the dividend across the top, making sure that every degree is represented. So I notice it's missing a degree 1 term, so I could think of this as 2x cubed plus 5x squared plus 0x minus 5. So my coefficients are 2, 5, 0, and negative 5. Make sure you don't miss that 0. I'm going to put a couple operator symbols so I remember what to do. Bring down the first term, and then do negative 2 times 2, which is negative 4. Add the numbers in that column to give me 1. Negative 2 times 1 is negative 2. Add those numbers in that column to get negative 2. Negative 2 times negative 2 is 4. Add those numbers to get negative 1. And then going from right to left, these numbers down here in my quotient are the remainder, the coefficient of x to the 0, the coefficient of x to the 1, and the coefficient of x to the 2. So the multiplication statement, basically we are able to break up the original dividend, 2x cubed plus 5x squared minus 5, into a product of the divisor times the quotient plus the remainder. So plus negative 1, I can just write that as minus 1. And you could expand this out to make sure that you got the right answer. 21 says fully factor this polynomial. And I have to write a full list of possible zeros, show a test, and the polynomial division. So to factor this, I first have to decide what to divide it by. So I need to divide it by something that is a factor of that, that's going to give me a remainder of 0. So based on the factor theorem, I'm just going to guess and check numbers, sub them in for x, until I find something that makes that polynomial be 0. But I don't just guess anything, I just guess factors of the constant term at the end. If there are integer values that make that polynomial be 0, they will be factors of 8. So it'll be plus or minus 1, 2, 4, or 8. And I just keep guessing and checking until I find one of those numbers that makes that polynomial be 0. And I can see pretty easily that p at 1, if I were to sub in 1 for all those x's, I would get 0. So I know that if I divide it by a factor that has a 0 of 1, so if I divide it by x minus 1, I would get a remainder of 0. So x minus 1 is a factor of that polynomial. So I need to divide that polynomial by x minus 1 to get it into factored form. We could do long division or synthetic division, right? Synthetic division works great when your divisor is degree 1 with a leading coefficient of 1. So I'll do synthetic division. The 0 of the divisor is 1, and the coefficients of the dividend are 1, 1, negative 10, and 8. To do the synthetic division, bring the first number down. 1 times 1 is 1. Add them. 1 times 2 is 2. Add them. 1 times negative 8 is negative 8. Add those numbers, I get 0. That's good. That means the remainder is 0, which means I'm on the right track. And these are the coefficients of x to the 0, x to the 1, x to the 2. So I can split the original polynomial into a product of the divisor times the quotient, right? This is just the multiplication statement form. So x squared plus 2x minus 8. And notice the question says fully factor, so I should look at the degree 2 factor, and it's a trinomial. I should try and sum and product factor it. There are numbers that multiply to negative 8 and add to 2. Those numbers are 4 and negative 2. So there's my fully factored form. P at x equals x minus 1 times x plus 4 times x minus 2. And the great thing about these questions, if you have the time, you could take the time, expand that out, and make sure it equals the original polynomial from the question. 22. Solve the following equation using any algebraic method. Well, this polynomial, it has 4 terms. You could try factoring it by grouping, but that's not going to work. So I'm just going to have to test for zeros of this again. So the possible zeros, well, since the leading coefficient isn't 1 this time, I'll test factors of the constant term divided by factors of the leading coefficient. So factors of 8 are plus or minus 1, 2, 4, or 8. Factors of the leading coefficient are 1 or 2. So do 1, 2, 4, or 8, each divided by both 1 and 2 to get a full list of all of the possible rational zeros of this function. So 1 plus or minus 1 over 1, 1 over 2. 2 over 1, 2 over 2, which I don't have to write because I already have 1. 4 over 1, 4 over 2. I don't have to write 4 over 2 because I already have 2. and 8 over 1, and 8 over 2, but 8 over 2 is 4, I already have that. So these are all of the possible rational zeros of the function. I just have to find one of them that works. If I do a test, I think actually, if I were to sub 2 into this function, it would make it be 0, which means that x minus 2 is a factor. So let me just quickly divide this by x minus 2. And I notice I get a quotient of 2x squared plus 9x plus 4. So I'm going to rewrite the original equation here. And remember, my goal is to figure out what makes this be 0. That's why I'm factoring it. Getting it into factored form easily lets me see what makes this equal to 0. So I can already write it into a factored form. It won't be fully factored, but it'll be the divisor x minus 2 times the quotient 2x squared plus 9x plus 4. I know that product would be 0 if either of those factors would be 0. The quadratic factor, I suppose I could do quadratic formula to figure out what makes it be 0, but that quadratic is also factorable, right? I'd be looking for numbers that have a product of 8 and a sum of 9. That would be 8 and 1, so I could split the middle term into 8x and 1x, and then factor that by grouping. Take a 2x from the first two terms, and nothing but a 1 from the last two terms. But that allows me to see that my three factors are x minus 2, x plus 4, and 2x plus 1. Now that's fully factored. What would make that product be 0 if any of those factors were 0? So what would make x minus 2 be 0 would be if x was 2. If x was negative 4, the second factor would be 0. And if x was negative a half, the third factor would be 0. So all of those are answers because each of those x values would make that whole product be 0, meaning it's a solution to the equation. And don't forget, you could check all of those answers in the original equation and make sure it makes left side equal right side. 23. Solve the following inequality using any method. Well, for a polynomial inequality, I like to solve those by graphing. So I'm going to start by moving everything to the left. And then if I want an accurate graph of this, well, I know it is odd degree and a positive leading coefficient. So based on that information, I know it's going from Q3 to Q1, right? Odd degree starts and finishes on opposite sides of the x-axis. So let me just start a little template here for where I'm going to sketch the graph. I know it's going from quadrant 3 to quadrant 1. And my goal is to figure out when is it greater than or equal to 0. So I don't know, when is it above the x-axis? Well, I want to know when is it going to switch from being below to being above, or vice versa. So I'm going to have to get it in factored form to find its x-intercepts. And I think this polynomial is actually factorable by grouping. If I common factor to 2x squared from the first two terms, I would get x minus 3. And from the last two terms, if I common factored a negative 18, I would get x minus 3. Since it's a common binomial, I could factor out that x minus 3, and I'm left with 2x squared minus 18. I noticed that second factor, I could common factor out a 2 from it, giving me x squared minus 9, which reveals the difference of squares, which I know x squared minus 9 would factor to x minus 3 times x plus 3. I have two factors of x minus 3. Let me combine those to a single factor that is being squared. Now that it's in factored form, I could state my x-intercepts for this function. I have x-intercepts at 3 and at negative 3. At 3, it's order 2. At negative 3, it's order 1. So let me plot those x-intercepts at negative 3 and 3. And then based on their order, I know that at negative 3, I should be going straight through. And at positive 3, I should be making a parabola shape, so bouncing off of it. And the question wants to know, when is this function greater than or equal to 0? Well, as long as I'm at negative 3 or to the right, the function is greater than or equal to 0. So my answer to this question, this function is greater than or equal to 0 when x is greater than or equal to negative 3. I want to include negative 3 because at negative 3 it's equal to 0. The next section, exponential and logarithmic functions. 24 says rewrite each of the following as a single logarithm and then evaluate. Round to the nearest hundredth if necessary. Well, the product rule of logarithm tells me that if I have two logs with the same base, that's important, that are being added, I can rewrite them as a single log, keeping that same base, but multiplying their arguments. So I have log base 5 of 28. And that means what exponent goes on 5 to get 28? It's going to be 2 point something. We want 2 decimal places of accuracy. My calculator tells me that's 2.07 approximately. Part B, before I use the product or quotient rule of logarithms, I should take any coefficients of logs and use the power rule, which tells me I can write it up as the exponent on the argument. So this would equal log of 8 squared plus log of 2 minus log of 4. I can combine the first two logarithms. They're both base 10, and they're being added together. I can combine them as a single log by multiplying their arguments. So 64 times 2. And now these two logarithms both have base 10, and they're being subtracted. So I can write them as a single logarithm by dividing their arguments. So I have 128 divided by 4. And that's equal to log of 32. And now I'm looking for what exponent goes on 10 to get 32. It's 1 point something. Let's use the calculator to figure that out. If I round to 2 decimal places, it is approximately equal to 1.51. Part C, I can use the change of base formula. If I have two logs being divided where the bases are the same, I can rewrite that as a single logarithm by taking the argument of the log in the denominator, 4, making that the base of the log, and take the argument of the log in the numerator and make that the argument of my logarithm. And now to evaluate this, I'm wondering what exponent goes on 4 to get 80. It's about 3.16. And of course, you could check all of those answers by typing the original questions on your calculator, and they should give you each of these final answers. 25, solve for x in each of the following equations. Round to 3 decimal places where necessary. Show all of your work. Check for extraneous roots where necessary. Well, a and b are both log equations, so I will have to check for extraneous roots for those ones. Part A, to solve this one, I'll want to start by combining those two logarithms. Since they both are base 10 and they're being added, I could write them as a single logarithm by multiplying the arguments. So x plus 2 times x minus 1 would be x squared minus x plus 2x, which is plus x, minus 2. Oops, and I can erase that extra equal sign I wrote there by accident. Now that I have it in this format where I have a logarithm equal to a constant, I can change this to exponential form. Remember, the base of this common logarithm is 10 if you don't see it. So what does this mean? It means that 10 to the power of 1 is equal to the argument. So that's what I write. 10 to the power of 1 equals x squared plus x minus 2. And now I just have a quadratic to solve, so I set it to 0 by moving the 10 over. And this quadratic, we could solve it using quadratic formula, or this one's factorable. The numbers that multiply to negative 12 and add to 1 are 4 and negative 3. The solutions to this equation are negative 4 and 3. Now, because we've used a logarithm rule that only works when an argument is positive, we need to check, are these both actually solutions? So we should check and make sure they both make the left side equal the right side of this equation to make sure they're both right. But there's a chance that maybe one of them makes one or both of these logarithmic expressions undefined if it makes either of the arguments be less than or equal to 0. And I can see that if I subbed negative 4 in for x, it would make both of those arguments negative. So it would make both of those logarithmic expressions undefined, which means it cannot be an answer to this equation. That's an extraneous root. If I subbed in x equals 3, yes, it would make that be 5 and that be 2, so they're both positive, so I know it doesn't make either of them undefined, but we should go the extra step and make sure it actually makes left side equal right side. So I would have log of 3 plus 2, which is log 5, plus log of 3 minus 1, which is log 2. Log 5 plus log 2, I could multiply the arguments together, so I have log 10. Log 10 means what exponent goes on 10 to get 10? That's 1. So it makes left side equal right side, so I know that 3 is a correct answer. Part B, I see ln of 2x minus 10. So ln of 2x minus 10, that's the natural logarithm. That just means log base e of 2x minus 10 equals 6. Remember, e is just Euler's constant. We treat it just like any other constant. I can change this to exponential form by saying e to the 6 equals 2x minus 10, and then just isolate x. So I have e to the 6 plus 10 over 2 equals x, and I want an approximate value rounded to 3 decimal places. I get 206.714. And once again, you can check that answer in the original equation. And notice it makes the left side equal 6, just like the right side, so that's a correct answer. Part C and D, we have exponential equations to solve, and there's going to be 2 different methods for these. For part C, it's definitely easier because if I look at the base of both of the powers, 4 and 8, it would be easy to rewrite those powers with a base of 2. So I could write them with the same base easily, so I'll start by doing that. 4 I could write as 2 squared, and 8 I could rewrite as 2 cubed. And then when you have a power of a power, you can multiply the exponents together. So 2 to the 2 to the 2x minus 5, multiply the 2 and the 2x minus 5 to get 4x minus 10. And the other side of the equation, 3 times x, I could just rewrite that as 3x. And now that I have power equals power, where the bases of those powers are equal to each other, I know that the only way the equation would be true is if the exponents were also equal to each other. So set the exponents equal to each other and solve. So I'll have 4x minus 3x equals 10. So x is 10. Part D, however, it would not be easy to rewrite 3 and 5 as powers with the same base. So instead what we'll do is we will take the logarithm of both sides. And then the power rule of logarithms tells me I can take the exponents of the arguments and write them as the coefficients of the logs. And then on the left, I'll do x times log 3 plus 5 times log 3. And on the right, I'll do 2x times log 5 minus 1 times log 5. And then I'll rearrange this equation so both of the terms that have an x will be on the same side of the equation. And both of the constant terms will be on the other side of the equation. On the left, I'm going to use a couple log rules. I'm going to take this coefficient and move it up as the exponent on the argument. So I have log of 243 plus log 5. And on the right, I notice both terms have an x, so I'm going to common factor that x from both terms. So that gives me 2 log 5 minus log 3. On the left, there's 2 logs being added with the same base, so I can write it as a single logarithm with the arguments being multiplied together. 243 times 5 is 1,215. On the right, I'm going to take this 2, move it up as the exponent on the 5, and then the logs are being subtracted, so I could divide their arguments. So I could rewrite that as a single log, as a log of 25, right? That's 5 squared, divided by 3. And now to isolate the x, I just have to divide the log of 25 over 3 to the other side. So it gives me log of 1215 divided by log of 25 over 3. And I could use the change of base formula to write those as a single logarithm. I would write it as log base 25 over 3 of 1215 is my answer for x. That's an exact answer. If we want an approximate answer, we could evaluate that on a calculator. That's about 3.350. So there's my final answer. #26 is a sound intensities question. It says the intensities of sound pollution were measured at a small airport runway and a local highway. The airport was 6,420.4 times as intense as the highway. So we have the ratio of intensities of airport to highway. So remember the formula for these sound levels is beta 2 minus beta 1 equals 10 times log of the ratio of intensities. So the question gave us the ratio of intensities. It says the ratio of airport to highway is 6,420.4. So I can replace that whole ratio with 6,420.4. It says the sound level of the local highway is 91 decibels. Well, notice the highway is corresponding to intensity 1, so I must replace beta 1 with the sound level of 91 decibels. And determine the sound level of the runway at the airport. So I'm basically solving for beta 2, just add the 91 to the other side. I get about 129.1 decibels. On to trigonometry. 27 says, suppose sine theta is 21 over 29. Well, a sine ratio, I'm just going to make a note here, is opposite over hypotenuse. And it tells me that the angle is between pi over 2 and pi. So I know it's in quadrant 2. State an exact value for sine of 2 theta. Hint, use an identity, don't solve for theta. So the intention of this question is to use the double angle identity for sine, which tells me sine of a double angle is equal to 2 times sine theta times cos theta. So I can evaluate sine of 2 theta if I just replace sine theta and cos theta with the ratios. And the question gives me the sine ratio for theta. It says it's 21 over 29, but I don't have the cosine ratio for theta. So let's see if we can figure it out with a diagram I'll make over here. Well, I know we're in the quadrant between pi over 2 and pi. That's quadrant number 2. So let me just draw a terminal arm in quadrant 2, connect it to the x-axis to make my right triangle. I know in this quadrant, only sine is positive based on Cast rule, which makes sense. I got a positive sine ratio, but cosine will be negative. The positive sine ratio is 21 over 29, so from the reference angle, I know opposite is 21, and hypotenuse is 29. If I use Pythagorean theorem, I could figure out the other side of this triangle is 20. So if this is theta, this angle in here, we could call it beta, it's the reference angle. I could figure out cosine of theta by doing the negative of cosine of beta, because we're in quadrant 2 where cos is negative. And cos of beta is 20 over 29, adjacent over hypotenuse. So I could say cos of theta is the negative of that. It's negative 20 over 29. And then I can just evaluate this, which is negative 840. In the denominator, I have 29 times 29, which is just 29 squared, which is 841. There we go. There's the ratio for sine of 2 theta. '28 says use a compound angle formula to find the exact value for cosine of 7 pi over 12. I need to know a few things to be able to do this question. First of all, I need to know my special triangles. So let me draw those quickly. And I also need to know my compound angle identities for cosine. I'll show you that in a minute. In order to find the exact value for cosine of 7 pi over 12, I need to change 7 pi over 12 to a sum or difference of special angles. So I have to figure out, is there a way I can add or subtract these angles to get 7 pi over 12? Well, maybe let me rewrite them with denominators of 12. So pi over 3 is 4 pi over 12, and pi over 6 is 2 pi over 12, and pi over 4 is 3 pi over 12. Hopefully you can see that if I do 4 pi over 12 plus 3 pi over 12, I get 7 pi over 12. So let me change cosine of 7 pi over 12 to cosine of 3 pi over 12 plus 4 pi over 12. And the reason why I do that is because notice when I reduce both of those angles, I get special angles. I get pi over 4 and pi over 3. And now I can use the compound angle identity for cosine. That compound angle identity tells me that cosine of a sum of angles is equal to cos of the first angle times cos of the second angle minus sine of the first angle times sine of the second angle. And now I can find all four of those ratios just by looking at my special triangles. Cosine of pi over 4 is 1 over root 2. I'm going to write the rationalized version of that, root 2 over 2. Cos of pi over 3 is 1 over 2. Sine of pi over 4 is root 2 over 2. And sine of pi over 3 is root 3 over 2. If I simplify this, do my multiplications first, I've got root 2 over 4 minus root 6 over 4. I can combine those to a single fraction since they have a common denominator and write this as root 2 minus root 6 all over 4. And let me show you how I can use my calculator to make sure this is right. Notice the approximate answer of cos 7 pi over 12 and root 2 minus root 6 over 4 is the same. So therefore I have the right answer. 29. Determine the solutions for each equation only on the interval between 0 and 2 pi to the nearest hundredth of a radian. Give exact answers where possible. If I want to solve an equation, I'm just looking for what value of x makes this true. I'm going to start by isolating sine x by moving over the root 3 and the 2. So sine x equals negative root 3 divided by 2. I recognize that ratio from a special triangle. Root 3 over 2. I can make a sine ratio of root 3 over 2 by using pi over 3 as my reference angle. Sine of pi over 3 equals opposite over hypotenuse, root 3 over 2. So I'm going to use pi over 3 as my reference angle, but I'm going to make sure to draw it in the correct quadrants to make the sine ratio negative. So let me do a little drawing here. Between 0 and 2 pi, I know I'm going to have two answers to this equation. They're going to be in quadrant 3 and quadrant 4, and those two answers are going to have the same reference angle. I'll call this answer 1, I'll call this one answer 2, and I need to figure out how far to rotate to get to answer 1 and also to answer 2, and those are going to be the two answers to this question. And like I said, they have the same reference angle. They both have a reference angle of pi over 3, and I got that from my special triangle. So my first answer, to get from the initial arm all the way over to the terminal arm at angle 1, I would have to go past pi by pi over 3. So I would have to do pi plus pi over 3, which is equal to 3 pi over 3 plus 1 pi over 3 is 4 pi over 3. There's my first answer. My second answer, I'll be looking for how far do I have to rotate to get from the initial arm to the terminal arm at angle 2. Notice it's pi over 3 short of going a full 2 pi. So I could calculate it by doing 2 pi minus the reference angle of pi over 3. So I have 6 pi over 3 minus 1 pi over 3, that is 5 pi over 3. There's my second answer. And any solving equation question, you can check both of those answers in the original equation to make sure it makes left side equal to right side. B. This is a quadratic trig equation, so I want to solve this by factoring it first. And since it's just two terms, and both terms have a cos x, I can just common factor this. Let me divide out a cos x from both terms. So take out a cos x. When I divide them both by cos x, I get 2 cos x minus 1. Now I'll set each of those factors to 0. Cos x equals 0, and 2 cos x minus 1 equals 0. And now when you have a cosine or a sine ratio of 0 or 1, you will want to be using your unit circle to figure out the answers to this. So let me just make a rough sketch of the unit circle. Remember, a cosine ratio corresponds to an x-coordinate on the unit circle. So if I can draw a terminal arm that intersects the unit circle at an x-coordinate of 0, which would happen here if I rotate pi over 2, or here if I rotate 3 pi over 2, I notice I intersect the unit circle at x-coordinates of 0. Therefore, cosine of pi over 2 and 3 pi over 2 are both equal to 0. So I have two answers for this. I'll call this x1 and this one x2. x1 is pi over 2. x2 is 3 pi over 2. And you could check those. If you do cosine of either of those on your calculator, it'll tell you it's equal to 0. How am I going to solve the zeros of the second factor? Well, I'll start by isolating cos x. Cos x equals a half. And if you remember your special triangle, if you use pi over 3 as your reference angle, cosine from pi over 3 is adjacent over hypotenuse a half. So we just have to use pi over 3 as the reference angle in the two quadrants where cosine is positive, just like our ratio. Cosine's positive in quadrants 1 and 4. So there's going to be a terminal arm in both of those quadrants, and both of those terminal arms I know are going to have the same reference angle. I'll call this answer 3, and I'll call this one answer 4. And they both have a reference angle of pi over 3 again. And then I'll calculate their principal angles. In quadrant 1, it's just equal to pi over 3. But in quadrant 4, to get from the initial arm all the way to that terminal arm, I would have to go pi over 3 less than 2 pi. So I can do 2 pi minus pi over 3, which is equal to 5 pi over 3. So all of my answers are pi over 2, 3 pi over 2, 1 pi over 3, and 5 pi over 3. 30 is proving a trig identity. When proving a trig identity, we separate into left side and right side. And our goal is to show that the two sides of this equation are the same for all values of x. That's what makes it an identity. And we can prove that by working separately on each side, rewriting them in equivalent ways to show that they're in fact the exact same function. And the identities we can use to prove this, if you look at the identity page here, we have lots of different identities we can use. I think I noticed in this question we have a couple double angle formulas, so maybe you want to pay attention to these identities here. We'll use those in this question. One of the double angle identities for cosine is I can change cos of 2x to 1 minus 2 sine squared x. And the double angle identity for sine is 2 sine x cos x. If I simplify the numerator, I've got 1 minus 1, so those are gone. And I'm subtracting a negative 2 sine squared x, so I can write that as positive 2 sine squared x. And now I can cancel those factors of 2, and I can cancel one of those factors of sine in the numerator with the factor of sine in the denominator. So I'm just left with sine x over cos x, which based on the quotient identity is equal to tan x. On the right, I could change tan x to sine x over cos x to show that these are in fact the same function. So I've proven to you that the left side is always equal to the right side for all values of x, so it is an identity. Last trigonometry question. We have the graph of a function, and we want to write a sine and a cosine function to describe that graph. Well, a transformed sine function looks like this format. We put the a parameter in front, we put k and d inside the argument of sine, and we put c on the outside. A cosine function for this graph is going to look exactly the same but have a different d value. Let's start by calculating a. We calculate a just by doing the max y value minus the min y value and dividing by 2. That gives us the amplitude of the function. Max y value is 1. Min y value is negative 9. So I have 1 minus negative 9 over 2, which is 10 over 2, which is 5. So the a value, or the amplitude of this function, is 5. K we can calculate by doing 2 pi divided by the period of the function. The period is the horizontal length of one cycle. I think it would be easiest if I mapped off between min values on this function to find the horizontal length of one cycle. So the period goes from there to here. That's the horizontal length of one cycle, so that's the period. And what is the length of that cycle? Well, the cycle starts at an x value of 0 and finishes at an x value of pi. So the horizontal length of one cycle is pi. So the k value is 2 pi over pi, which is 2. The c value is the horizontal midline of the function. So to find the middle of the y values, we just add the max and min y values and then divide by 2. That finds us the average y value. So 1 plus negative 9 over 2 is negative 4. And notice if I drew a horizontal line through negative 4, that would cut the function in half horizontally. The last thing we have left is the phase shift, the d value. And the d value will be different depending on whether we're doing a cosine or a sine function. If I'm doing a cosine function, I'm just looking for what is the x-coordinate of a maximum point. Well, the x-coordinate of that maximum point, well, what's my scale? Every 1, 2, 3, 4, 5, 6 units is pi, so each 1 unit is a sixth of pi. So the x-coordinate of a max is at 1 pi over 6, 2 pi over 6, 3 pi over 6, which is pi over 2. The d value for sine is the x-coordinate of a rising midline. So the x-coordinate of that point right there. If I want the x-coordinate of that point, I can't tell exactly where it's at, so I'll do a little calculation. I know the horizontal distance between that point and a maximum point is always pi divided by 2 times k. So in this question, our k value is 2. So it equals pi over 2 times 2, which is pi over 4. So the distance between the d value for sine and the d value for cos is pi over 4. I know the d value for cos is pi over 2. I'm interested in the d value for sine. I'm interested in this value right here. To get to that, I would have to subtract pi over 4. So I'll do the d value of cos minus pi over 2k. d cos is pi over 2 minus pi over 2 times 2, so minus pi over 4. So I have 2 pi over 4 minus 1 pi over 4, that is pi over 4. So I can just go ahead and write my transformed equations just by subbing into my transform sine or cos function. I'll do the cosine equation first. It would just be 5 times cosine of 2 times x minus pi over 2 minus 4. The sine function is going to look exactly the same except for the d value. The d value for sine is pi over 4, not pi over 2. And there we have it. There's 2 equivalent equations. They should generate all of the points that make up that red function. You could test out a few points that we know are on the red function and make sure both equations would be able to generate those points to make sure you have it right. Last section of the exam is on rational functions. It says graph f at x or g at x, not both. I'll just do them both quickly. I'll do g at x first. G at x is a reciprocal quadratic. So I'm actually going to write some information about the quadratic function x squared plus 2x minus 8. And then I'll use that information to state some properties of 1 over x squared plus 2x minus 8. The quadratic function, I could factor it to x plus 4 times x minus 2. So I know its x-intercepts are at x equals negative 4 and 2. I know its vertex is going to be in the middle of negative 4 and 2. So if I add those and divide by 2, I get negative 1. So the vertex is at an x-coordinate of negative 1. So if I wanted a good shape of this quadratic, I would make sure that I centered the vertex and then chose points on either side of it, making sure to include the x-intercepts. And then I could sub each of those in and calculate y for each of those x values of the quadratic. And let me do a quick sketch of the graph of this quadratic. And now let me graph the reciprocal of this quadratic. Well, a reciprocal quadratic, I know it's going to have a horizontal asymptote at y equals 0. And it's going to have a vertical asymptote at any places that make the denominator 0. So what makes the quadratic be 0? Well, we solve for that over here, negative 4 and 2. So it's going to have vertical asymptotes at x equals -4 and at x equals 2. And then I can make a rough sketch of this reciprocal quadratic. It's going to look like this, same intervals of when it's positive and when it's negative. And I know it's going to be approaching the asymptotes at the extremes. But I'll get some more accurate points to be able to sketch it a little bit better than that. I'll make a table of values by keeping the same x values as I did for the quadratic, and then just do the reciprocal of the y values. So in this table I'm making in red, those are the points for g at x. I should have written g at x in red here. And I can get those points by just doing 1 divided by the y values I got from the x squared plus 2x minus 8 function, because g at x is just 1 divided by that function. So I'll just do 1 divided by each of the y values I got in the blue table. And I'll plot all of those points. And there we have it. In red is my g at x function. Let me clear all this and sketch a graph of f at x. The f at x function is a quotient of linear functions. I can find the horizontal asymptote just by dividing the leading coefficients. 2 divided by 1 is 2. Vertical asymptote, what makes the denominator be 0 would be -1. So I'll sketch those. And I also want the x-intercept of this function. So I'd set y to 0 and solve. And if I solved this, I would get x equals 2. So the x-intercept is at 2. And to find the y-intercept, I would just set x to 0 and solve, and that would give me -4. Now, I know quotient of linear functions are hyperbolas, where I will have a branch in this quadrant and a branch in this quadrant. But I can graph those a little bit more accurately. Let me actually get a third point on the branch in the lower right quadrant. Let me find another point. Let me just figure out what's the value of y when x is 1. If I sub 1 into my f at x function for x, I get -1. So there's another point, 1, -1. So let me draw this branch. And I could easily draw the other branch just by translating these 3 points to be over here in this quadrant. So let me just first look at this point, 0, -4. Where is it in relation to where those asymptotes cross? It is 1 to the right and 6 down. So let me do the opposite of that. Let me go 1 left and 6 up. If I go 1 left and 6 up, 1, 2, 3, 4, 5, 6, I get a point right here. Let me do that same thing for this point. From where the asymptotes cross, it is 1, 2 right, and then 1, 2, 3 down. 2 right and 3 down, the opposite of that is 2 left and 3 up. And then my last point, from where the asymptotes cross, it's 1, 2, 3 right, and 1, 2 down. So that'd be 3 left, 2 up. And then I can connect them, making sure to approach the asymptotes. And there we go. There is my f at x function. And here is the last mandatory question of the exam before we get to the choice questions. For this question, it says solve this inequality. So I would start by, because it's a rational inequality, move everything to one side. I would combine this to a single fraction by getting a common denominator. So this 1 over 1, I will multiply top and bottom of it by x minus 1. I'll collect my like terms in the numerator. And for this function, I could sketch a graph of it, but I think I'll make a factor table for this one. In the factor table, I'm going to need to know what the x-intercepts and the restrictions on this function are. So the x-intercepts are what makes the numerator 0, so x equals 4. The restrictions, what makes the denominator 0, x can't be 1. I'm going to make a factor table now which uses those x values as its dividing points. I'm going to write each factor of the equation in a row. And now I'm going to pick an x value within each interval. Between negative infinity and 1, I'll pick 0. Between 1 and 4, I'll pick 2. Between 4 and infinity, I will pick 5. And now I'm going to check each of those test values. Do they make my factors positive or negative? Well, 0 makes both of the factors negative. So in my equation, I'll have a negative divided by a negative, which is a positive overall sign. If I sub 2 into x minus 4, it's negative, but if I sub 2 into x minus 1, it's positive. So I'll have a negative over a positive, which is negative. If I sub 5, it makes both of the factors positive, which means the overall function will be positive. The question asks me, when is this function greater than or equal to 0? So it's positive between negative infinity and 1, and also between 4 and infinity. So that's how I'll generate my answer. My solution would be two intervals. It would be the intervals of x values between negative infinity and 1, or between 4 and infinity. Notice I included a square bracket at the x value of 4, and that's because I want to include 4 in my answer. At 4, it's an x-intercept, which means y is 0 at 4. And I want to know when is the function greater than or equal to 0, so I want to include 4 in my answer. I don't want to include 1 because the function doesn't even exist at 1, which is why we have a round bracket at 1. Alright, lastly, we have 4 application questions, and you're required to choose 3. I'll quickly show you the answer to all 4. Choice 1 says to find all the solutions for the equation cos of 2x equals root 3 over 2, and I only want to find the solutions on the interval between 0 and 2 pi. Give exact answers where possible. Well, I know for this one I will be able to give exact answers because I recognize this ratio root 3 over 2 as a ratio I could make from a special triangle. Let me just remind you of that special triangle off to the side here. And before I actually use that special triangle, I'm actually going to, for this double angle equation, I'm going to replace that double angle. I'm going to say let 2x equal k. And then I'm going to rewrite this equation and solve it as if I'm trying to solve for k. So my new equation would say cos not of 2x, but instead of k equals root 3 over 2. And then this equation to solve that will have a positive cosine ratio. So I'm going to sketch a Cartesian grid. And I know cosine is positive in quadrant 4 and quadrant 1, so I'll have an answer for k in both of those quadrants. I'll draw a terminal arm in both those quadrants. And the principal angles to get to those terminal arms will give me two answers for k, k1 and k2. Now I want a cosine ratio of root 3 over 2. And looking at my special triangle, I know cosine from pi over 6, adjacent over hypotenuse, would be root 3 over 2. So I will place a pi over 6 reference angle in quadrants 1 and 4, and then get the principal angles to both of those. In quadrant 1, my answer is just going to be pi over 6. But to get to the answer in quadrant number 4, I would be pi over 6 less than going a full 2 pi. So to get my second answer for k, I can just do 2 pi minus pi over 6. So my second answer for k is 12 pi over 6 minus 1 pi over 6, which is 11 pi over 6. But remember, those k's are actually 2x's. So I'm going to replace those k's back with 2x. So I'm going to have 2x equals pi over 6, and 2x equals 11 pi over 6. So really what I'm trying to figure out is what angles can I double to get pi over 6 and 11 pi over 6. So I'm just going to isolate those x's by dividing the 2 over. So my first x, pi over 6 over 2, is pi over 12. And my second answer, 11 pi over 6 over 2, is 11 pi over 12. Now these are both answers to the original equation, but they're not the only answers between 0 and 2 pi. Remember, the equation we're working with is cosine of 2x. That's a cos function that's been horizontally compressed by a half. The period of this function is only pi. So the two answers we got are in the first cycle. Let me just do a really quick sketch of this function so you can see what I'm talking about. So notice between 0 and 2 pi, this function does 2 cycles, and we're interested in when is that function equal to root 3 over 2. Root 3 over 2 is, I don't know, like roughly up here. It's going to be equal to root 3 over 2 at pi over 12 and 11 pi over 12, but then also again here and here. We need those two answers, and we can get them by just adding the period of our function to our original two answers. So to get my third answer, I can just add the period of the function, which is pi, to my pi over 12 answer. So x3, 1 pi over 12 plus 12 pi over 12 is 13 pi over 12. And I can get x4 by adding the period to my second answer. So I'll do 11 pi over 12 plus pi, and that gives me 23 pi over 12. There we go. There's the 4 answers to the original equation, and you could check them all in the original equation to make sure they're right. Choice 2, we're solving an exponential equation that is of quadratic form. So I actually am going to rewrite this a little bit. I'm going to rewrite it as, instead of 4 to the 2x, I'm going to rewrite it as 4 to the x squared, just so you can see that that is a perfect square value. Minus 2 times 4 to the x minus 15 equals 0. I'm going to use a let statement, kind of just like we did for the last question. I'm going to say let k equal 4 to the x. And if I do that, my equation becomes k squared minus 2k minus 15 equals 0. And that's nice and easy to solve. It's just a 3-term quadratic. I can factor it using the sum and product method. Multiplying to negative 15 and adding to negative 2 are negative 5 and 3. Set each of these factors to 0, and I get two solutions. I get k equals 5 and k equals negative 3. But remember, those k's are actually 4 to the power of x. So I can resubstitute in 4 to the x for these k's. So I have 4 to the x equals 5, and 4 to the x equals negative 3. And then when solving for an unknown exponent, we can use a logarithm for that. If I want to know the value of x, which is the exponent that goes on 4 to get 5, I can use log base 4 of 5 to get me that value. And if I want to know what exponent goes on 4 to get negative 3, that exponent would equal log base 4 of negative 3. Well, I know this isn't going to be possible. No matter what exponent I put on 4, it's still going to be positive. And another way I know this isn't possible is because the argument of a logarithm has to be positive. So I know for this one, there is no real solution. But log base 4 of 5, well, that's going to be 1 point something. I'll have to use my calculator to figure that out. I get about 1.161. Next question, choice 3. Given this polynomial function, f of x, solve for k given that f of x divided by x plus 1 has a remainder of negative 6. Well, I can use the remainder theorem, which tells me if I sub the 0 of the divisor, so the 0 of x plus 1 is negative 1. If I sub that in for x into my polynomial function, the answer will be the remainder. So the answer will be negative 6. So I can set that function equal to negative 6 if I sub in negative 1 for x. And now I just have to solve this equation for k, and it's the only unknown. So negative 6 equals 1 plus 2 minus k minus 5. Negative 6 equals negative 2 minus k. So k equals 4. And that's it for that question. And the last choice question is just to calculate some limits from a graph. I want to find the limit of f of x as x goes to infinity. So as this function goes forever to the right, what does it look like the y value is approaching? Well, it's approaching the y value of the horizontal asymptote, which is at 2. How about the limit of f of x as x approaches negative 2 from the right of negative 2? So notice there is a vertical asymptote at an x value of negative 2. As the function approaches that vertical asymptote, from the right side of that vertical asymptote, the function seems to be going infinitely low. So the function's y values are approaching negative infinity. But as we approach negative 2 from the left of negative 2, the function's going up to positive infinity. because the function as x approaches negative 2 is not approaching the same finite value, we could say that the limit as x approaches negative 2 of f of x does not exist. And that's the end of the exam. Hopefully this helped you out.